Hey guys, thanks for tuning into CMTEQ channel in the series of tutorial on IDMT Relays calculations. Well, before we can just get started in these calculations here, if somebody has to ask you what is an IDMT relays, from the top of your head, what are you going to say? Well, we can see that it is a relay, right? So what does it do? It provides protection. What kind of protection? It provides an overcurrent protection. And you can also just give the meaning of IDMT, which stands for inverse definite minimum time relay. Now, why is it inverse definite? Well, it is inverse because the operation of an IDMT relay is inversely proportional to the amount of current that is passing. So which means if you have a high current passing onto your line, then the IDMT relay, which is an overcurrent relay, which is also based on timing of operation, will trigger much faster compared if you have less current passing, right? So it's basically incorporate also an operation of a fuse, right? So a fuse will blow up much faster if there is a high current passing through. It will just instantly blow up. A slow blow fuse will just overheat as the current start to rise, and before the current can get to the set maximum, then the fuse will blow up. So that is basically what an IDMT relay is. Now I've got a couple of tutorials where I've extensively explained this piece of equipment that is widely used in power system. So in this tutorial, we're just going to see how to calculate some of the basic settings and characteristics to ensure that your IDMT relays is fully operational. Now, in order for you to understand and solve a problem, right, an engineering problem, you have to read it carefully and understand what actually they are asking, what are they requiring you to do. And that way you don't miss the very important detail. So without any further ado, I will say, please, if you like this tutorial, gives it a thumbs up. Like right now, just click the thumbs up and also subscribe to CMTEQ channel so that you don't miss more tutorial of this nature in the future. So what I was saying here is you have to read the problem statement. So this is how the story goes. A feeder CBA with an in-feed at C has 3 motors connected to the bus bars at A. Okay, so now we've got 3 bus bars here. That's CBA. Now on bus bar A, we've got 3 motors. Okay, and we've got another 2 motors that are connected on bus bar B. Right now, the fault level at A and B are 1000 amp and 1400 amp respectively, and each motor has a full load current of 20 amps. So this is the current that each motor draw when it is running. Okay, now standard IDMT relays, each with a pickup current of 110% of settings, are used to provide overcurrent protection at C and B. Keep in mind, now this is important, to provide overcurrent protection at C and B. Why not at A? Right? Why not at A? But the protection are provided at C and B. Why? Because this is where those relays are attached. Now, the characteristics of the relays are given by the formula. TC is equal to 3 over log M. Now, this is the IDMT relays inverse characteristics formula. This particular one is the normal inverse or the standard inverse. We've got the extremely inverse and the very inverse characteristics as well. Now, all the CTs have a ratio of 120 over 1 amp. So which means basically you will have 120 amp on the primary and 1 amp on the secondary of your CT. So the starting current of each motor is 6 per unit, right? The grading margin is to be at least what? 0.4 seconds. Okay, so that is the minimum time of operation for each relay. So that is the grading margin. Now, assuming that only one motor is to be started at a time, okay, and that the starting surge lasts for 5 seconds. Okay, now you need to draw the network layout and determine the suitable current setting for the relays, the TMS for the relays at B and C, okay? That is where the overcurrent relays are situated, where they need to operate, okay? If the operating time for the relay at B is to be 0.5 seconds, okay? So now you've got a different operating time for the relay at B compared to the relay at C, right? Where we have a grading margin of at least 0.4 seconds. So you have to take account of all of these details that are given so that you don't miss anything and get confused somewhere. Now, C, the suitable TMS, so the time multiplier setting for the relays at C, if one of the motors at B is replaced by a bigger one, okay, the full load current of which is now 50 amps. So now we know that at the beginning of the problem, they say the motors, they've got a full load current of about 20 amps. Now after doing all the calculations here at A and B, they're now telling you, well, what if you replace one of the motor with a 50 amp full load current? Then calculate the TMS again. So this is the bottom line of this problem. So now let's get going. So the first thing we do here is obviously we need to draw the network layout. So the network layout is as follows. So this network layout basically just describes the problem statement. So just make sure that it actually reflects what they're saying here. Okay. So what do we have here? This here is where the in-feed is. Okay. So this is where the power is coming from. Okay. So that's the in-feed. Now notice this relay here on bus bar C is going to be looking out on the fault on B and also on the fault on A, okay, on bus bar A and B. And relay B will be looking out on the fault on A. But relay A, which is now standing here, and there is no other bus bar on the outbound here, so that basically means this relay here will not be protecting anything because we do not see anything on the other side. So this is how you have to ensure that you understand this network layout. So the first question here, A, is the current settings for the relays. Okay, now which relays? We got 3 relays here, but the question says that overcurrent protection is only provided at C and B. So that will be these 2 relays here. Okay, so we only need to focus on the current settings for relay B and relay C. Now, it's important they mention in feed at C. So that means power is coming from this side. So this is where the power is flowing from. So power flow from here to this point here as per the arrow indication. So that means that relay C is providing protection for A and B. In case something happen on A and B, relay C is going to cut off the power, right? And relay B will be doing that for the relay at A. But relay A will not be protecting anyone here. There is nothing on the other side as per our network. So we do not have to worry about relay A settings because there is nothing outbound. Then we move on to relay B. Now, relay B, remember the setting currents is based on the load that the relay is seeing. So that basically means here, forget about the fault here. We know that the fault current here on at A is 1000 amp. But right now we are concerned about the current settings for the load. Okay, we do not want this relay to trip when the motors are running, okay, or when they are starting. We don't want anything like that to happen. So this means then we have to take account of the statement that they say here, okay, 3 motors, okay, and they got 20 amps of full load current, and they can start up to 5 seconds, the timing duration of the startup. And there is a 6 per unit current that must be multiplied with the full load current so that we can get the full startup current. So this means we then have to calculate the setting current for the normal condition and the overload condition. Now the overload condition will give us the maximum current at this point here. That will be 160 amps, right? Why 160 amps? Because we are basically assuming 2 motors are already running, so that will be 20 times 2. And then the 1 motor is starting, that will be 20 times 6. and this gives me 120 plus the 40, so I get 160. So this is the highest, because at start, if only one motor is starting, the other motor is off, we can only see that we only get 120 amps of current down here if one is starting, and that will only last for 5 seconds. And then assuming now the one motor is now running and the second one is starting, and that will also just give us 120 plus the 20, and that will give us 140. So which means the highest current we can get is when two motors are running and one is starting. And we do not want the relay here at B to trip for that 5-second time period. Okay, so then we know the normal load will then be 60 amps. So that's basically 20 times 3. Okay, so now we can go ahead and calculate the plug settings, because remember, the setting current is obviously for the plug setting here, because you want to move this plug, right? You want to move this plug from here to different settings so that you can set up the current for your disk there. Okay, now we move on. No load condition. Now the no load condition, we've got the I no load divided by 0.9 times CT ratio times IN. Now I've explained this formula already on a couple of tutorials. Please, you can catch up, then we don't have to repeat what we've already said here. Okay, so which means here we can then just go ahead and replace the values. So that will give me 60 times 0.9 times 120 over 1, because that's a CT ratio. And we've got the nominal current. It's always the secondary current of your CT, so that will be 1 amp. And that gives me 0.55. So which means the plug setting here will be 55% tap. Then we can go for the overload condition. Now the overload condition, now remember the 1.1 here is the 110% settings for the pickup current. So that is where the 1.1 come in. And then we can go ahead and calculate that as well. Now the I overload is now 160. Then we've got a 1.21. Okay. Then we can have a plug settings to be at 121%. So this basically means we can select the highest settings among these two here. So that would be 121. But because 121 setting does not exist, so we can take a 125 settings, which should be somewhere here for our plug settings. Right, now we can go ahead and find the plug settings for the relay at C. Now the relay at C, as we know that per the problem statement here, is protecting bus bar A and B. So which means the overload or the normal load condition that this relay is going to see will be the maximum current that will flow from this point. And this current here will depend on how much is being pulled here and how much is being pulled there, right? And this here means that for the overload on bus bar C, we're going to consider one motor is already running and the other one is starting, because there's only two motors here on bus bar B. First, that's an immediate one, and that will give us 140 amps of current. But then we have now to add the load, right, on bus bar A, assuming that these three motors are already running. So that will be contributing to the overall overload that bus bar C is going to see. So that is going to be 60 amps adding to the 140. Then we're going to have a total overload of 200 amps. But now, here is a trick. This 200 amps here is not the worst case scenario here, because these two bus bars, they are independent of each other, right? So these are feeders, okay? So we don't know what is happening here. We don't know what is happening here, right? So this is a network. This could be long lines, kilometers of cables. So, but this relay here at C must ensure that it does not trip to whatever is happening there. Now, assuming that at the time where the two motors are running and also the one motor is starting, where we know that we're going to have a current of 160 amp flowing here. And also we have a similar condition of one motor running, one starting, which give us a current of 140 amps. So which will give us an overload current here. We can see a total overload current that this relay will see will amount to 300 amps. So that will be like a worst case scenario. But here we just took a assumption that things are good there, they're already running. Okay, no one is starting motors there, they're already running. So which means we just take account of that load, and then we get the total overload that this relay will see. So that gives us a 200 amps. So this means the normal load that this relay will then see is then going to be the two motors here. That will be the 40 plus the normal load that is running at 60 amp on this bus bar. So that will basically just be the 100 amps. So that will be 2 times 20, that's 40, and 3 times 20, that's 60. So that's 100 amps of normal overload for relay C. Then from here we can calculate the plug setting here for our relay at C. Okay, so the first one, the normal condition, will then give us this value of 0.92. Okay, then which means it's a plug setting of 92.6%. Then we move on for the overload condition. So the plug setting will be I overload divided by 1.1, again the pickup current settings. Then we get a 200 over 1.1 times 120 divided by 1 times 1, and that gives us 1.51, which is 151%. And again, always take the highest from these two calculated plug settings. So this will give us a plug settings of 175%. So you're going to move your plug setting from all the way to somewhere in there at 175%. Now we move on to the next question, right? So the next question is to what? Calculate now the suitable time multiplier setting for the relays at B and C. Now that we've got the current settings for this relay, we set a plug setting. So that basically means until now what we've basically done is the network here is going to operate. Okay, nothing is going to trip, it's going to run smoothly and will be fine. Okay, but we did not take account of the timing in case of a fault current. Okay, because we know that these overload are only lasting for 5 seconds. But what if we now got a huge surge current that is now going to be passing through like a 1000 amp on bus bar A here, and then we got a 1400 amps on bus bar B. So what then should happen? So this is where we need to calculate now the time multiplier settings for the relays at B and C. Now they even gave us already here by saying that we need to assume that, okay, the relay at B is to be 0.5 seconds. So that is the operating time for the relay at B. Okay, that is this relay here must operate at 0.5 seconds. Now the procedure here is very simple. So we first going to calculate the TMS, okay, for this relay B for the fault on bus bar A, and we then going to calculate the actual operating time of this relay for the fault on bus bar B. So that is for the fault on its own bus bar where the relay is situated. Okay, so this then basically means relay B for the fault at A, we then call this multiple of settings M, and that is equal to I fault divided by the CT ratio times IN times the plug settings. We already calculated the plug settings, so we can then just go ahead and replace here. We know what the fault current is, it's 1000 amp, and everything we have, so we get a M of 6,667. And we're going to use this multiple of settings to then calculate TC, okay? And then we're gonna use TC to then calculate our TMS, which is actual TA divided by TC. Alright, I said everything there. Now we know that this relay operate in 0.5 seconds, so that is important. So that means TA is actually 0.5 seconds. So if you miss this part here, that basically means you're gonna get a wrong answer. Okay, then we can calculate our TC, which is this characteristics curve, that is 3 over log M. Okay, so that is the standard characteristics or normal inverse characteristics. So that gives us a TC of 3.641 seconds. Okay, then we can move on. TMS is TA over TC. Okay, we got our TA already here. Then we have a TMS of 0.14 seconds. This is important. Now remember, this TMS here is based on this relay to react on the fault on bus bar A. Now we need to calculate the actual time that this relay needs to react based on the fault on B and also based on the fault on A. But the TMS that we're going to use to calculate the actual time is based on the fault on A. You have to understand that. Okay, and then we move on. So the relay B for the fault on bus bar B. So basically the same formula here, and we then find a multiple of setting of 9.33. Then we use that to calculate TC. So we find TC 3.093, and then we can then calculate our TA. Okay, and again this TA is the actual tripping time for this relay whenever a fault occurs either on A and B. Okay, so TA is TMS times TC, so that gives us 0.14 times the 309 that we just calculated there for TC. Okay, and that gives us a TA of 0.43 seconds. So this is the actual operating time for this relay here at B. Okay, that is when he has to protect bus bar A and bus bar B as well. So now we can move on and calculate the TMS and the actual time for the relay on bus bar C. Okay, so that is relay C. Now it is important that you remember that this relay C here is basically the in-feed relay, so which means you have to take account of the grading margins. Okay, now forget about here, they say that this relay B has to operate on 0.5 seconds. Okay, so that is a specific relay, but for this relay C, they're not saying anything to you. That means you need to take account of the grading margin. Now I discussed about the grading margin on my earlier tutorial on these IDMT relays, so please ensure that you can watch that tutorial and get yourself up to date. Okay, so now we're moving on here. So the relay C for the fault on bus bar B. Okay, so that is now this relay trying to look out for this fault here, which is 1400 amps. So basically what we're going to do here is we're just going to calculate a multiple of settings, and we're going to find exactly the same thing. And the reason being that look more like a coincidence here. We've got a bigger current here, 1400, and we've got a bigger plug setting. So we find a multiple of settings of 0.666, whereas for the relay B on the fault on bus bar A, we had a 1000 amp of current, and then we had a plug setting that was 1.25, and that also give a 6.667 multiple of setting. So we can go ahead and calculate then our TC. Okay, that will be for this relay. So the TC will then be 3 over log M, so that is 3.64 seconds. Then we can go ahead and calculate the time required for this relay to operate to be TA plus the time that is the operating time for this relay B here. So we're now adding the grading margin of 0.4 plus the operating time of this relay, okay, before this relay can react. Okay, so that gives us a TA of 0.83. Then we can calculate our TMS to be TA over TC, and that gives us 0.228 seconds. Okay, so now we can go ahead and move on to the next question, which is to calculate TMS settings, okay, for these same relays here. But this time around, they are now telling us there is a bigger motor that is now added here, okay, on bus bar B. Okay, one of the motors at B is replaced with a bigger one. So we know that we had 2 motors on bus bar B. Now one of them have been replaced with a full load current of 50 amps. So basically they're just telling us here that we need to calculate another plug settings for this relay on C, so that it does not trip, since there is now a different load on bus bar B altogether. So we need the overload current that this relay is now going to see, since there is a change here. Remember, we had the 200 amps, okay, of current that we saw that will be coming at that point here, being drawn from here to there. Now that was for all the motors being 20 amps full load. Now there is a one motor with a 50 amps full load, so that means that overload current is then going to change, okay? So which means the overload will then be the 20 plus 50 times 6, okay? So this is now on this bus bar B. One motor is running, the other motor is being started, okay? Then we can take the 60 amps of the other bus bar here, okay, assuming that they all running, and we can add it to the 320 here, okay? So that will then give us an overload current, okay? So that is going to be 380 amps. So we move from 200 amps to 380 amps here on this bus bar here. So we also need to ensure that this relay here does not trip because of that change in the overload current. So we can go ahead and calculate our plug settings once again, okay? So the overload condition, the same formula, so we now have a new current, so we got now a 288. We know that the maximum plug setting we actually have is 200% on the tapping there. So we can just ignore that and just select the 200% plug setting, which is the highest, okay? Then we can then move on, okay? Now, the relay C now for the fault at B. So now this is now the TMS, since we now got the plug setting, which is actually the setting current. So now we can then calculate now the new TMS for this relay, since now there is a different plug setting for this relay, okay? So this will then give us the formula. So that is 380 divided by 120 over 1 times 1 times 2, okay? So the 2 here is for the 200%. So that gives us a M of 1,5833. All right, so then we use that to then calculate TC. And with this TC, we can then move on and calculate TMS. But now it is important to take account of the surge time. The surge time, so that is the 5 seconds startup time that the motors take to start. And during that startup time, we've got this high overload current of 380. So which means if we are going to calculate our TMS here, we must take account of that longer period of time, and that is going to give us the maximum allowable surge time, okay, that we can actually wait before we trip, okay? So having said that, our TMS here is going to be TA divided by TC. So our TA is the 5 seconds, and then we go to TC, then we find that 0.33 seconds for our TMS. So guys, this is it for this tutorial. I hope you've learned something. If you have any question, please drop it in the comment section. You can drop a comment and I will attend to them as soon as I have time. Please and give the thumbs up for this tutorial and subscribe to CMTEQ channel. And stay tuned for more tutorial of this nature. Until next time, cheers.